Let's talk about the 2018 activity. There have been previous collapses at the summit, a handful in the 1800s, but the one that occurred in 2018 was the largest one that we know of in the past, that's been recorded in the past 200 years. And unfortunately, the Lower East Rift Zone eruption has the distinction of being the most destructive eruption in Hawaii in the past 200 years. Over 700 structures were destroyed.
So what was happening before that eruption? This shows the 2 months before the eruption. Throughout March and April, swarms of earthquakes were happening. These are groupings of earthquakes close together in space and time. Each time you see one of these, some of them are noted by these purple bars, was a swarm of earthquakes. And what was happening at the time, the volcano was engorged with lava. We were seeing inflation at the summit, inflation at Pu'o'o. The lava lake overflowed in late April. And in fact, when that happened, there was a very, very productive swarm of earthquakes, these shallow orange ones right here in the Upper East Rift Zone connector, that little sliver on my earlier map. And that really heralded a big change that was about to happen. We didn't know what was about to happen, but on April 30th it happened. And that was the collapse of Pu'o'o.
Pu'o'o, around 2:15 p.m., had this massive swelling or inflation. And then it collapsed on itself. So this is the cone, and it made this typical pink ash plume for many days that week and several weeks after. That inflation that happened for about 15 minutes cracked the west side of the cone. And it was pretty rainy that day, so we couldn't see anything on our cameras. The thermal camera caught a little bit, but we ended up taking a helicopter out the next day to see what had happened. This was a huge signal that had never been seen to that magnitude here before.
Later it was verified that yes, the lava lake was there and it had drained away, and this used to be full of lava. Where did it go? Well, it went down to the East Rift Zone, and this is the simple view of it, and so it was here, it drained down and went that way. And as it did that, it produced a lot of earthquakes. So this is an example of 1 day's worth of earthquakes observed at one station in the Middle East Rift Zone, known as Joka. May 2nd, it turns out, this is the day before the eruption began. And the idea here, if you look at this cartoon, is that there is a finger or a blade of magma underground. You can think of it, it's called a dike, and it's pushing its way through cracks, and it's forcing its way to make bigger cracks, to open up new space. And each time it does that, it makes an earthquake. Earthquakes happen when rock breaks. And so that's happening right at that tip, right at the front. And basically we can map out where the front of that dike is as it moves. And that's what we were doing. So from that, we had a good catalog of earthquakes that helped characterize where that dike was at any given time. And of course, if there were going to be changes in the eruption. So this is a video put together by our colleagues over at PTWC and using our data. So that's one of the swarms that happened in mid-April that I talked about earlier under the summit. And you can see these were going on, keeping us quite busy, I should say, even before the eruption started. These are the ones in that Upper East Rift connector that really were right before the eruption began, before Pu'o'o collapsed. And here we go. There it is. And there they go. Did you notice them moving east? And that's the 6.9 earthquake, which we'll talk about in a minute too. But this is the beginning of the eruption and what the earthquakes were doing. And just notice how they moved east. They kind of stopped here and they went more east.
This is the rest of the afternoon of April 30th. After about 2:30 p.m., there was earthquakes that started migrating down rift. Whatever happened at Pu'o'o, whatever failed underneath it, allowed magma to move forward down into the lower rift, which is down here. On May 1st, we see that earthquake front migrating to the east. And then on May 2nd, it stops just short of our station WAPM, right under the subdivision of Leilani Estates.
So this is showing the progression of earthquakes from Pu'o'o in the west, down here, all the way to Leilani in the east, up here. So southwest, northeast. And if you look at the slope of this, so this is distance versus time here. So you can't quite see it's cut off, but this is May 1st, May 2nd, May 3rd. So over a period of about 2 days, it travels some 20 kilometers or so. This is about the speed you could walk, just a comfortable walking pace. So now we know how fast that dike was moving underground just by plotting this up. But notice how this line was pretty steep and then it rolled over and got flat. That's because the dike decided to stop where it was. It stayed right there in this spot, which happens to be right there under the neighborhood of Leilani and its surrounding area. And then on May 3rd, that's when the eruption began. Even we saw a little bit of the shallowing of earthquakes right before the eruption, where they started off a little bit deeper, they get a little bit shallower as it came to the surface.
During this 3 or 4 day period, the entire middle rift zone and part of the upper rift zone was losing material in the subsurface to the lower rift zone, which was becoming engorged. The other thing that started happening on May 2nd was that surface streets in Leilani Estates began to crack. And at first it was 1 crack, and then it was 2 cracks, and then it was 5 cracks, and then it was 10. And we realized this is going to happen fast. And again, the ground is swelling up as material is moving under Leilani Estates. The next day, on May 3rd, we have some more earthquakes in the same area. And Fissure 1 opens that evening, around 4:30 p.m.
This is a short video clip taken on May 5th, so a couple of days later, but it's illustrative of the kind of activity that happened in those first weeks of the eruption down in the Lower East Rift Zone. Blade-like bodies of magma reached the surface and formed a line of spattering vents, as you can see here. And the lava was rather viscous and sort of sticky. You can see these amazing bubble bursts and spatter not rising very high, lava moving away from these vents a few tens of yards.
The next morning, literally at 1 a.m. the next morning, Fissure 2 opened, and the next few fissures, all the way to Fissure 6, opened sequentially downrift, right to about where the earthquakes had stopped progressing forward.
Right in the middle of that was the magnitude 6.9 earthquake on May 4th. This was the shaking pattern, the shake map from that earthquake. So you can see it was most intense down in the Kalapana area, lower Puna, and less so the more up the chain you go, up the island. And so the earthquake occurred here. Those aftershocks made this circular pattern offshore. And the interpretation of that is that this fault area, this really low angle, almost horizontal fault between the oceanic plate below and the volcanic material above is what was ruptured, and basically this whole thing was immobile, producing earthquakes, and still is to a certain degree today. When the magma was withdrawn from the upper part of the East Rift Zone and the middle part, it went to the lower East Rift Zone, and when it did that, it had to wedge its way in, and when it forced its way in, it put sideways pressure on the rock. Okay, and what this is showing is a net loss of material here in the Middle East Rift Zone and a net gain of material down the Lower East Rift Zone from one of the models that's come out of this. Another view of that, a sideways view, if you could just slice into the volcano, as that magma was going in, it was pushing sideways, and that pushed the whole south flank to the south. It might have been ready to go anyway, but this was the push it needed to get started, and it moved along that almost horizontal fault. Seismologists have taken this data as well as GPS data, even tsunami data and other data, and they've created models of how the fault ruptured. These are just 2 examples from the literature. All the hot colors, the red, orange, yellow, show where most of the motion occurred along that surface. So it starts off here, but it kind of twists around and moves in these 2 kind of lobes here and here, which is the interpretation right now based on the available data. Some seismologists are arguing about the magnitude, by the way. We still think 6.9 is the best representation, but some people taking in other data think it's 7.2. And it's, these things sometimes change with further interpretation. We don't know if that will happen, but with the 1975 earthquake, it started off as a 7.2, and now we think it's a 7.7, for example. So it's not unprecedented to think that. So this earthquake was felt statewide. More than 500 kilometers away, all the way up on Oahu and even on Kauai. Was there damage? And so the answer is yes, but no one was talking about it. And for a good reason. There was an eruption going on. People were evacuating their homes at this time. It was a very high-intensity crisis going on. This is one of the news articles about the earthquake, mentioning a power outage, mentioning some of its effects. For example, this rock slide or landslide happened off Chain of Craters Road, near the end of the road. A collapse of Pu'o'o was triggered, one of many, but this one was ascribed to the earthquake that day. These cracks in Leilani were reported by the residents as being due to the earthquake. There was a tsunami as well, was observed statewide. It was 40 centimeters in Kapoho, about 30 centimeters in Hilo, all the way to about 5 centimeters in Kauai. So the aftershocks were very plentiful and are continuing to this day to a certain degree. And you can see just by eye, these are all the larger ones, magnitude 2.7 and higher, that occurred during the first month or two after the earthquake. And again, there's that elliptical area that you can see quite clearly. This is interpreted as the toe of that area of the fault that's pushing its way seaward. It spans about 435 miles. Now, one of the other models of slip is shown here, which also agrees roughly with where the earthquakes occurred. So we think there was about 5 meters of movement of the flank of the volcano during the earthquake alone. The 6.9, of course, was the main shock of the sequence, of the series. But you don't know that when a sequence begins. There was a 5.1, and then the next day there was a 5.7, which felt even bigger, and then an hour later the 6.9 happened. And so it became the main shock. That was relegated to be a foreshock, and then a number of other ones happened after in the magnitude 4 range. So you had the 6.9, the decay down, just kind of a nice decay down, and then. But remember, I told you that the activity is elevated now compared to what it was before. See how before we were getting maybe 100 earthquakes per week, and now we're getting about 200 earthquakes per week. And that's because that south flank of the volcano is still very mobile compared to what it was before. It's still wanting to slide, it's still settling, and it's producing more earthquakes than it would otherwise.
It didn't seem to affect those 6 fissures that were opening up, or those 5 fissures that were opening up that day. They just carried on with their sluggish spattering as if nothing was wrong. On May 6th, after Fissure 6 was done erupting over here, Fissure 7 opened up the next morning, right next to Fissure 2, and then the vents started opening up back uprift, with the exception of 12 that jumped the line and went back downrift. But in general, the trend was an uprift migration.
This is from May 4th to May 9th here in this part, no movement in terms of east or west movement. The earthquakes just stayed where they were. They were happy to be right there. They were parked there. All the early fissures were opening up. But notice this. So right there on May 10th, it pushed its way eastward more. This was that next phase of the eruption beginning. And it's just really interesting. Again, just notice this really nice curve. So the earthquakes were down here at this depth, 3 kilometers. They pushed up to the surface at 0 there, and that's when they moved eastward. There was that first pulse I told you about. It settled down for around a week. It made that second advance that we just talked about on the previous slide. It settled down and stayed there for the rest of the time. Seismically, we saw a first pulse of earthquakes, this first phase, followed by a brief pause in seismicity, or a relative pause. The second phase came up next. This is when it pushed eastward more, and the magma eventually got hotter. Fissure 8 took over toward the end of this, and the rest is history. Now, one thing that's really interesting is right about May 18th, the seismicity rate drops off. That's about the time that Fissure 8 is going to take over. The path has been cut, is the interpretation. The conduit is open. The rocks don't need to be broken anymore, so the earthquakes die down. But the tremor doesn't die down. So if you recall this cartoon from earlier, at the front of that dike was where the earthquakes are happening. But behind it, in the conduit, the magma is resonating and sloshing around, and this creates this tremor phenomenon, which is a lower frequency kind of hum that occurs, which we can also track. Here's a map showing tremor.
There were 2 days of pause, May 10th and May 11th, where we thought, is that it? Are we done? Or is there more coming? And we assumed there was more coming because the earthquakes started migrating downrift again. And they didn't go that far downrift, but they went far enough that we thought, okay, the next fissures could be downrift. And sure enough, Fissure 13 opened here, 14, and then the rest opened sequentially downrift. Fissure 17 is offset. It's the only one offset majorly on the whole trend. May 14th to 18th. The rest of the fissures up through Fissure 23 began opening uprift again. So the thought is that the earthquakes came down, something was preventing them from moving further, the dike was able to kind of fill that crack that they had created and erupt in here, and then the earthquakes were able to break open the rock and free up some more space, and the magma moved down here. Once that couldn't move forward anymore, it starts filling up and backing up uprift. You have multiple fountains along a single crack, erupting magma. that is producing a lava flow moving quite quickly down from Fissure 20 and around into a subdivision. And it covered this area, which is probably a kilometer or a little more in distance, within minutes to an hour. It was moving very fast. So much so that the helicopter pilot and I actually got out on one of these side roads at the cul-de-sac, and I called civil defense, and he went and warned a few people who were still home that they needed to leave, because this was coming at them very quickly. So from May 18th, when our geophysics kind of goes quiet on the lower rift, to May 27th, right, as Fissure 8 reactivates, we have a series of uprift reactivations. Fissure 17 on May 18th, 19th was going strong. It had an 80-meter tall fountain. Fissures 16 and 18 were also active. 20 and 22 were starting to send their flows down to the sea. They did that in a day and a half. As Fissure 17 started to shut down, Fissure 19 and 15 started to reactivate. And then I noticed as 16 and 18 appeared to shut down, turns out they never quite shut down, but as they decreased activity, Fissure 6 and 13 started to increase activity, and they produced a joint lava flow that also went to the sea. And then as Fissures 20 and 22 started to shut down, 23, 21, and 7 started producing a flow, and 21 and 7 together sent a flow to the north towards our geothermal plant and to the south. I think had it not filled this pit crater here, it would have reached the sea as well. But quite a bit of volume went into this pit crater first. And then, as everything else shut down, 6, 13, 23, Fissure 8 reactivated on May 27th, and with that came the new Fissure 24. And once that started flowing and effusing a lava flow, Fissures 7 and 21 just shut down as well. During that time of reactivation, as the lower vents shut off and that pushes magma to come out of the next available upper vent, we saw what's called a graben form. And that is, if you think of a keystone in an archway, a graben is essentially that kind of a shape, and it drops down as magma ascends. This one is fairly small. It's 100 meters or a football field across, but it dropped about 2 meters or a little over 6 feet over the course of 2 or 3 days. And the reason that these grabens form is when magma is trying to rise, it has to push the walls apart. And so just like a keystone helps keep a doorway intact, the ground surface will drop and behave in much the same way as it's being pushed apart, so the lava can reach the magma can reach the surface. I should mention, that this is LiDAR based, because it's a little too fine scale for the INSAR derived image, but you can kind of get a hint of it. There's a few blue spots in the same trend there. This, like I said, this was 100 meters across, 1 football field across. It was several kilometers long. It stretched essentially from Pohoiki all the way to Highway 130 through the whole subdivision. So here's what that looks like. Over the course of a little more than 24 hours, and prior to this, it had been just a hairline crack, turned into a 1 or 2 foot crack, and 6 inches, 12 inches of down drop to 6 or 8 foot wide crack and 3 or 4 feet of down drop. And like I said, it ultimately reached about 6.5 feet of down drop. This happened very fast. Actually, the residents stopped me in the middle of one of my shifts and say, "Is the ground sinking?" Yes, actually, the ground is sinking. That was our cue that a lot more magma was about to come out of whichever fissure it chose as the easiest path. That was Fissure 8. And it was active for 2 months. It started, its first rejuvenated flow May 27th. It lasted until August 5th. In this picture, which was taken a month into that time frame on June 26th, you can see how long and how wide it is right here. This red line is a half mile wide, or 800 meters across. The flow came up Luana Street and then made a bend to the northeast here in this picture.
And this amazing river of lava traveled all the way about 11 kilometers to the ocean and produced the devastation that we know happened down in the Lower East Rift Zone. On June 3rd, the lava flows first reached Kapoho Bay and began to destroy so much of that lovely community.
It went 8 miles, or 13 kilometers, until it reached the sea, and it did that in 5 days. So the average eruption rate for those 2 months was approximately 100 cubic meters per second. And to put that into terms that we might recognize for those of you who've come to these talks a lot and think about Pu'uo'o a lot, Fissure 8 erupted 5 years worth of Pu'uo'o material in 2 months.
You get a sense just from the size of this channel and the rate that lava is flowing through it that these were very high eruption rates 50 to 100 times greater than what we observed during the previous years of Pu'uo'o activity. That high eruption rate was draining magma from the summit magma chamber, causing the floor of the caldera to drop. And this is a time-lapse camera that we had near Kapoho, looking north and showing the drop of this section. You know, this used to be flush with this, and it dropped over 100 yards. Other sections around Halemama dropped much more.
Looking off towards Halemama, you would have seen these occasional explosions that look like this. These are the largest explosions that we'd seen at the summit since 1924. So what was happening is that while that lava was erupting down in the Lower East Rift Zone, 25 miles away from the summit, the roof of the volcano was basically falling in steps because of withdrawal of magma from the summit reservoir complex. And each one of those collapses produced a scene like this, where the ground actually dropped 3 or 4 yards, and of course rocks were clattering down all the steep caldera walls, liberating dust that you see here. There were 62 of these events that happened over the course of the 3 months. And each time there was an equivalent of a magnitude 5 earthquake that was produced. And so residents in the summit area can well remember what that felt like, the ground shaking with regularity.
Now listen. That's not wind. See the dust? So it's rising. The dust would just fill the scene, and it would take a while to settle out. So every 30 hours or so that would happen.
To give you a sense of the topographic changes at the summit, this is what the caldera looked like before the 2018 eruption, taken in early 2018. After the eruption, this is what the caldera looked like. So we had this section, this downdrop block that sank in a piston-like manner, and then we had enlargement and deepening of Halemama. So I'll go back and forth here and you get a sense of what changed.
Here's a time lapse. You may have seen this, but it never gets old. It's 1 image per day. Tens of thousands of earthquakes happened to allow those faults to move, that allowed that deformation to take place. So this was the 2018 eruption. This is what was so unusual about that eruption. That amount of earthquakes has never been measured before in Hawaii, 20 times higher than the normal rate. I'll zoom in on that a little bit. Here's that eruption. It was 3 years of earthquakes in 3 months. Here they are, May, June, and July mostly. Also August right there. So if we plot the earthquakes on a map from the eruption, there are 3 main sequences or groupings of these earthquakes. The first one, the Lower East Rift Zone or LERS grouping, occurred down here during the first 2 weeks or so of the eruption. You can see earthquakes per week plotted, and you can see mostly these 3 weeks is when the story was going on right there, and we'll talk about why in a minute. And it tailed off. The second topic is the south flank. So this is this large area, if you recall that rectangle I put up there before, but it also extends offshore quite a ways. And you can see earthquakes showing up out there as well, related to the 6.9 earthquake. And finally, really the big story is the summit, with all of these earthquakes shown in blue, some, almost 50,000, depending on how you count them at the summit during the eruption. So what were the earthquakes doing? There were a lot of earthquakes in the summit, some 40, 50,000 at least. And these were characterized by a cycle. This is showing earthquakes per hour. Starting on May 17th, one of these plumes happened. And with that was this blip on the tilt record where it kind of raised up and then dropped back down. And this happened again and again and again. At first, they were kind of small in terms of energy release and in terms of numbers of earthquakes, relatively speaking to what happened later. And then things really started to pick up. But this cycle happened 62 times. It peaked at about, let's just say, 150 earthquakes an hour. That's 5,000 a day or so. And also, quite surprising, it stopped very abruptly. We interpret these as stepwise collapses as the magma is draining away. The caldera just falls slowly in between and then abruptly falls during the collapse. Basically, if a collapse just happened, it's happy, it's resting on the magma below. There's no gap there, and everything's good. So this is showing the earthquake rate being low. And over time, though, the magma is draining away. It's like pulling the plug on the bathtub. And now that floor of this part of the caldera is no longer supported. Okay, there's a void underneath it, at least a partial void. And these wiggles show that earthquakes are happening to help, because the faults are getting stressed to try to hold this up. But the strength of the rock is only so much. Eventually they give, and this is a big collapse happens. It falls down. So this is lower than this. See? And now the caldera is at a lower spot. And then it's stable for a few hours, and then it happens again. So this is a day's worth of earthquakes at one of our stations. This is, if you watch the data on our website, you would see a similar kind of plot. You can see lots of earthquakes swarm right there, and then it collapses. It's happy, it's quiet for several hours. Maybe you get some sleep, no more shaking. It picks up again. Each time a collapse happened, the scene was like this. Who knows what that is? It's HVO. So poor HVO building up there getting battered. Cars would bounce. Cars in that parking lot there, they would bounce it several inches. So obviously it created cracks, it created damage. This is what the sign looks like today. Inside it knocked things over. There's some bookcases. Sinkholes. This one was in front of a golf course, but there's sinkholes in the park too. Kīlauea Overlook is one of these right in the entrance to it. Buckling in the road from minor buckling like this, it shows that there was compression here, to major buckling like this. And this is a downdrop of 20 feet maybe, and taller than a car, certainly not drivable. And this is what the scene is like all around the west side of Crater Rim Drive.
So this eruption was dramatic. It produced a lot of devastation. It was very tragic for a lot of people on the Big Island. It was tragic and challenging for HVO to monitor well and provide good information. But it was also a scientific gold mine, and we can't ignore the fact that we accumulated an enormous amount of information by tracking and studying that eruption. But to hit on some of the high points of what we learned, some of you may remember that at the start of activity in May of 2018, we stood in this room and talked about what happened in 1924 at Kīlauea. And we thought that was because as the magma column drained into the volcano, that groundwater was able to flush back into the system and produce steam-driven explosions. So we talked about how that was likely to happen. We did have explosions, but instead of being driven by groundwater rushing back into the hot core of the conduit, we now think that it was more likely volcanic gas accumulating and pressurizing beneath the rubble that was filling in that collapsing column and occasionally blowing out material to form an explosion. Groundwater was really not part of the process. And the reason we think that is that a lot of the material that came out was actually magma itself. Lava was involved. Each time one of these explosions happened, there was a big burst of volcanic gas. So it seems more like gas was the culprit and not groundwater. Another really important insight was looking at what was going on up here at the summit. We have all these different tools that we were using. These tools allowed geophysicists to look very carefully at the collapse process and really make a model of what was going on underground to cause the collapse that we saw at the surface. So this collapse through time is shown in that little movie. So by looking at the changes at the surface and the shape of that collapse, and modeling all of the data from these different instruments, Kyle Anderson and his colleagues have determined that the collapse at the summit started very early in the withdrawal process. Only a few % of the volume of that summit magma reservoir, which is about a mile below the surface here, was drained by the time the collapse began. And that was really surprising to us in retrospect. I think the paradigm had always been that you had to have wholesale withdrawal, really emptying of that chamber before the roof would start to fall in. And that was clearly not the case. So that was an important result.
So one of the really interesting observations from this is that with these tens of thousands of earthquakes, there really were only a few dozen that were unique. So, and by that I mean we've seen repeating earthquakes where you can compare the shaking pattern of one earthquake with the shaking pattern of another earthquake on two different seismograms. These are different earthquakes. They actually have almost the exact same shaking. And the interpretation is it's really the same fault moving, just a repeat of what happened before. And what this is showing, these orange lines are the 62 collapses through time from May to August. And all the red bars are the little families or clusters of these earthquakes that were similar. So there was a family that started here. It picked up for a while. It went off. It started again. It went off, and it went for several days, maybe a week, before this other one took over, and this other one. And so you can see some of these last a week, some of these last a month, and but they don't last forever. We can also look at that same information in a depth profile. So these colors, now the colors show each of the different families. So this red color shows, well, that cluster or family only occurred at this depth, maybe half a kilometer depth. This purple one is right at 1 kilometer depth. So these are those repeating earthquakes, and they're repeating because it's the same fault structure failing the same way over and over again until the geometry of the crater changes so much that can't happen anymore. And this is that same data. This is those same colors, in fact, showing after you carefully relocate all those earthquakes, most of them actually, if you look on our website, it'll look like a buckshot on the caldera. But when you carefully relocate them, they mostly actually occur along that boundary where the downdrop area happened. By the way, this little animation is showing with time how they bounced around different areas of the caldera. So earlier on they were in the west, later they were in the east. When every collapse happened, they didn't feel like normal earthquakes, right? They felt like you were on a ship, like you were kind of rocking. Each one of these lines is one of those 62 collapse events. So this is May, this is August. And I've put a square around these because don't these look a little different than those? So those first ones were really, really long period, as we say. They didn't have much of the jolt or the high frequency shaking, right? In fact, some people couldn't even feel them. And they were very subtle. And in fact, that comes out when we can actually compute different kinds of magnitudes. There's not only one magnitude, there are different kinds. So if we compare a long period magnitude to a short period at high frequencies, low frequencies, all of those plot down here. So they are like this. They're self-similar, they're scattered, but they're all in this range. And what's interesting is all the other ones that happened starting from May 29th onward are all up here. Much tightly clustered, by the way. So two different processes are going on with these types of earthquakes. And by the way, those later ones from May 29th on were the ones people felt a lot more strongly and widely. And these are the 5.3s that everybody talks about. These were 4.7s. Still big, but lacking at high frequencies and therefore didn't cause a whole lot of damage. So that was one observation. Now, if you look carefully, you can notice other stages in there as well, which we think are related to the kind of the rotation of this piston block as it goes down. Another just first-hand observation of the data is this is energy, okay? So moment is a fancy word for energy that we use. Notice how all those first events, this is from May 17th to 29th, okay, those first 10 events were right here, really low energy release, okay? But something happened on May 29th. It shot up, and the next several events were up here. It went back down, and it sort of settled out, and all the rest were more or less the same out here. So there's basically three phases going on. So there's that first one, which is those really low frequency ones that only some people could feel. There were these second ones, which we think is when this, what's called a ring fault, this circular or semicircular fault around the caldera was actually forming. And then this last one, it's formed already. It's sliding down episodically. And the lower plot, by the way, is the time between each collapse. Okay. Time between the collapses. So in the beginning, it was kind of scattered, but mostly low. Okay. So 10 to 40 hours, a pretty big range, but lower than this. So basically when that ring fault was forming, it took longer between events. And why is that? My idea is that it's breaking more rock, it's having to do more work, and so it takes longer to fail during this time, up to 60-something hours in between events. Once that had happened, a nice surface has been formed. It can slide along that. It came into this nice steady pattern about 30 hours between events, which crept up over time but was pretty consistent. Why is it so consistent? I think the interpretation is just that the magma was draining out very consistently. So this is controlled primarily by how fast the magma is going away. In the beginning, there was a lava lake. It drained away. Once it had all drained away, you started to see collapses as the actual magma chamber itself started to drain away. And the vent where the lava lake had been was still open. And that's why the plumes were getting out. Each time a collapse happened, it would kick up a lot of material and would get out. But that got blocked at some point. And once it was blocked, really there were no more plumes happening, but it was still collapsing. The ring fault had formed mostly in the west, and in the east it seemed to grow over time.
If we look at this Pu'u'o era, we had about 1 megaton per year, which is 1 million tons of sulfur dioxide per year. And then that lava lake opened up at the summit, and things jumped, especially early on, at least 2 million tons a year of sulfur dioxide that was being emitted. Then we hit 2018, 10 million tons or more of SO2 came out. For context, the so-called dirtiest power plant in the U.S. that emits SO2 in Ohio is not even 1 million tons a year. So that's about this red line. So that's obviously a record breaker in terms of Kīlauea since these kind of measurements began in the late 70s.
Another important thing we learned down in the Lower East Rift Zone, we saw patterns in the eruption that had never been studied quite in such detail before. By looking at all of the data and comparing it with what we were seeing elsewhere on the volcano, what Matt and his colleagues now feel is that these long wavelength, 1 to 2 day surges in output were absolutely responsive to the collapses going on up here at the summit. And it had implications for hazards, because when we saw the collapse at the summit, we learned that within minutes, and certainly peaking within hours, we would see an increase in output in the Lower East Rift Zone. So we were able to be on the lookout for overflows of the channel or potentially a new breakout from the lava river. The shorter time scale changes in output were likely due to very shallow outgassing processes. And the proposal in this paper is that the magma, as it's coming to the surface to erupt, develops gas segregation areas or foamy regions. And so for a time, the magma coming out might be extra rich in gas and more foamy, kind of like the head of a beer or a soda can when you pop it out. And during those times, you actually have less molten material flowing into the channel. Other times, the magma is less frothy. It's denser, and it will come out at a greater rate.
This is a video. He sped it up 5 times. And you can see that at times, Fissure 8, which is here, is sending a lot of material through this spillway into the channel, which starts about here. And we're getting some convection. It looks like turbulent flow. And then after 5 or 10 minutes, remember this is sped up, so it's going to be a few seconds here, it slows down. And we start seeing more crust, and we lose our turbulent eddies, and they're almost all gone except for that one. And it stays like this, nice and calm and flowing a little more slowly. And then it'll speed up again. And Matt finally wrapped his head around it and was able to figure out that this is very similar to a process that we've seen before called gas pistoning. The only difference is that gas pistoning, when we've seen it at Mauna Ulu and at Pu'u'o and at Halemaumau, it's confined. It's in a pit. And so you see the lava rise up, and then when the gas can finally break the surface, the gas all comes out and the lava drops back down. And so it's a cyclic rise and fall of a lava surface, depending on the gas buildup and the gas release. But if you're in a fountain that has a spillway where lava can leave, and it's not confined, it manifests itself a little differently. Matt was able to figure out that as the fountain height goes up, more SO2 comes out of the fountains, and the seismic tremor goes up. As a result of that, the lava level in the channel goes down, and the bulk effusion rate goes down, and the velocity of the lava in the channel goes down. But when the fountains start to wane and come back down in height, the SO2 kind of stays trapped in those fountains a little longer. The seismic tremor goes down. The lava level in the channel goes up because all of that material, instead of going up and releasing the gas, is now coming out and over into the spillway. So the bulk effusion rate goes up and the velocity in the channel goes up. And this happens on the order of minutes. Roughly every 10 minutes or so, you can see this change happen. Sometimes it's more dramatic than others, but this seems to happen on a cyclic pattern, just like gas pistoning. So here's a video of that. This is the low flow time where the fountains are high, just off the screen. Higher, they got about 50 meters around this time. And then you'll see it's starting to speed up again. And the lava is reaching higher because the fountains are dropping and is coming down the spillway faster, so it banks up and builds up these ramparts in the back here. So we can use gas pistoning to help explain this behavior in the lava channel that, for a while during the eruption, was kind of enigmatic for us. This eruption was unprecedented for Kīlauea in the past 200 years of its activity. The total flow field area, which is in pink here, was 13.7 square miles. The new lava delta area, which this is the old shoreline that's dashed here. So this area that extends out into the sea is 875 acres. If we look at the Kapoho Bay and the first part of the delta that formed there, it's pretty darn flat. So I'm not worried about lava that filled in the bay collapsing, per se. It's not until it reaches the edge of the shelf and drops down to deeper levels in the ocean that it starts to approach this slope. This lava flow, even though it's not off flow, is going to behave a little differently than the Pahoehoe, which is oversteepened onto this slope. We haven't seen any cracks form in the Kapoho delta, nor did we during the eruption. Maybe one crack. The other interesting thing that we notice is that right here, the channel would just flow straight into the ocean. It's not interacting with the water. It's not exploding. It did on a few occasions, but fairly rare for the whole eruption. And it went out. This is a real bathymetry profile of pre-eruption and from boats who came by to do surveying. So it went out, 2.5 kilometers from the edge of the old coastline. And so the thought is, where is all this material going? And many of us at HVO asked that. Where is all this material going? And why isn't it exploding when we know these little tiny things can cause explosions from Pahoehoe deltas? And so what I realized is that this is actually inflating and kind of lifting up out of the sea. This is shortly after the lava entered Kapoho Bay. We're going to focus on this feature here. It's got a peak in the middle and 2 dips. We're going to try to track that through June. So here we go. Put an arrow there to help. It's going to get more and more subtle as time goes on, but it's here. And I want you to focus on this next lobe that came out and formed a new part of the delta. And we're going to look at what happens to the water in between these two. So in this picture down below, it's here. And then on June 11th, a few days later, it's here. And on June 14th, it's isolated from the ocean, and it's actually slightly higher than the ocean. June 15th, not much change. June 22nd, it's evaporating away, and it is, 1 or 2 feet above sea level at this point. So that's something that I don't think we've ever seen in a Pahoehoe delta, where it kind of lifts up from the sea as opposed to piling on top and going into the sea and diving down. And then the last example I have of this is from July. This was the coastline the day before, and then suddenly this, quote-unquote island appeared. But really, this just kind of rose up. It's connected to the delta underneath. There's only a couple feet of water here. And it's erupting lava. It's still the Fissure 8 lava. It's just come down through the delta underneath and back up. And so again, we have another example of something kind of rising up as opposed to piling on top and diving down. The point is that this is a cohesive flow as it extends underwater, whereas the Pahoehoe is just onlapping layers and layers. And so perhaps this is actually a more stable delta anyways, even though it already has a more shallow slope to begin with.
And the final lesson or insight I'd like to share is it was just recently published in a paper by Cheryl Gansecki, a Hilo professor and colleagues, and it has to do with the chemistry of the lava that was coming out in the eruption. What Cheryl and crew discovered by looking at the chemistry of lavas that we sampled almost every day over the course of the eruption is that the first material that came out was actually material that had been stored in the rift zone for many, many decades, maybe going back 100 years. But why did it erupt? Because there was fresher material coming into the rift zone beneath it, adding heat and gas and causing it to be remobilized to the surface. And then as the eruption progressed, these pockets of older material, they mixed with fresher material and ultimately were flushed out such that the final material coming out of the volcano in the eruption was very fresh material that probably came from up the rift zone and even the summit storage area.
So it turns out there's certain key elements I'm going to be talking about. I like to think of it as a magma is like a bag of trail mix, right? It's basically a big mix of elements. together. And if you think your average magma trail mix, right, it's mostly peanuts and raisins, and it's got some good stuff. It's got some M&Ms and some cashews. Some trail mixes might have something weird. Maybe you got broccoli chips or something that nobody's going to want to eat. Okay, so our magma's got a little bit of everything. So now we picture our magma sitting there beginning to crystallize. Things are being removed. So we hand our bag of trail mix over to our friend Olivine. Olivine loves M&Ms. Starts eating out all your M&Ms. I get some of the peanuts and other stuff too, but eats out a lot of your M&Ms. Passes it on to some of the other crystal friends, right? They really like M&Ms too, maybe some cashews. And they're eating a little bit of other stuff. But by the time you get the bag back, there's a lot less material, and it's really concentrated in peanuts and raisins. All your M&Ms are gone, and nobody touched the broccoli chips. Okay? So, in our analogy here then, zirconium is our broccoli chips. Nobody wants it, right? It just gets left behind. Magnesium and calcium, that's our M&Ms and our cashews. Crystals love them, they want to eat them up, they go away pretty fast. And so those two guys are kind of two different fingerprints, and they're going to tell us different things about our magma as we go. The top one here is our zirconium, right, our broccoli chips, versus our M&Ms, the magnesium. And this little gray zone right here, this is the last 10 years that have erupted out of Kapoho. So as soon as those first lavas erupted, we got the samples back, we stuck them in the machine, I got the first numbers back, and I was like, yes, it's exactly what we thought it was going to do. High zirconium, low magnesium. This is not your Kapoho magma that's coming up. This is something different. This gray band is the average Kapoho temperatures from the last few years. So they're up at about 1150 Celsius. This initial 15 fissures erupted at about 1110. At this point, though, the lavas were just kind of slow, kind of sticky. But we were already pretty sure that what we were looking at was stored magma from previous eruptions. So here's in green is our new lava flows. There's a change between those initial fissures and the second group of fissures, right? Things are they're hotter. It's about 20 degrees hotter on average. Right away we could see that. And when we look at the fingerprints, we see, okay, it's starting to shift more towards Kapoho-like compositions. It's likely that what's happening is this old sticky stuff is getting mixed up with some hotter stuff coming down the pipeline, and it's starting to shift. Now, kind of starting at the same time, fissure 17 broke open, and when we look at the temperatures, they're very, very low, around 1060 to 1080 down in here. So what does that mean? It means our lava is very cold, very viscous. Suddenly, it makes a little more sense why it's so explosive. But then we go into phase 2. So somewhere around May 17, 18, things really start to heat up. And so we've got these big flows, we've got a bunch of these lava fountains active. Lava's becoming faster moving, it's becoming more fluid. So it's dramatic increase in volume. When we look at the chemistry now, and here's the blue, we're seeing it's basically approaching Kapoho values, although it sort of veers off a little bit there. And our temperature-wise, we're coming up to Kapoho values. So we see that it's going towards Kapoho, and then it veers off to this higher magnesium. Zirconium basically flattens out, right? We're done with the broccoli chips. But for magnesium, there's something going on here. We're getting too much. Temperature-wise, it all levels out, pretty much stays the same magma temperature the rest of the eruption. Notice that it's a little bit lower than Kapoho. And the reason for that is that magma had to travel an extra 10, 15 miles down the pipeline to get to the surface. And in that time, it cools off a little bit. The other thing that happens in here is these little purple dots. So while fissure rate was going, right, that everything is kind of pouring out, you've got this very hot, very fluid lava, there's a couple of these other fissures get reactivated. So they suddenly will kind of do little eruptions that would spit out a little bit of lava, mostly very small scale stuff. When we got some pieces and took it back to the lab, we saw, oh, look at that. These don't look anything like fissure 8. These look more like what we were seeing over here. Even one of them, fissure 22, even looks kind of like the andesite. We've got here this end member of the andesite, very high in potassium and zirconium, but not so much in titanium. Whereas our high titanium here, the Leilani stuff, the early stuff, is kind of in between. And these make separate bodies, but they sit on this trend that makes sense. If you take a magma, you let it crystallize and take out the crystals, that's the path it's going to follow. But our little purple things sit over here. So they're not on that path at all. They're telling us a story about mixing of those magmas. So not only do we have the stored magmas, but somehow in the system, they're getting mixed up with each other. So this diagram was our kind of one of our attempts to try to visualize this. So this is like the phase 1 stages where they're all erupting separately, and then they begin to mix. And while Fissure 8's going down here, a little bit of this andesite seems to be mixing in with some of this other stuff and giving us these in-between eruptions. Clearly there was some connection at depth. Now, what are those magma bodies, right? We've got these 3 end members. This, of course, is whatever's coming from the summit and Pu'o'o. And these 2 guys, though, have to be these stored magma bodies. Now, where do they come from? There's a lot of possibilities. We basically just modeled a late 1955 as a possible parent. It works just fine for either one. So, one of the big questions left on this then is, how long can magma sit down there and still be eruptible, right? Still be fluid enough to get back to the surface? So under PGV, back in 2005, they drilled into a magma body, another one of our possible sources, the dacite magma body. Something even more unusual, but it never reached the surface, and it couldn't reach the surface. But it's still a possibility for one of the things that might be contributing to our unusual compositions. We tried modeling it, but you couldn't really get our magmas directly out of that one. It doesn't really work, so I don't think it's actually involved. Those olivine crystals floating in there, this is going to be about how much magnesium is in your olivine. Right here in gray, those are the lava lake samples. Whoa, had a little bit more variety. That's these little black triangles, but they're all pretty closely matched in chemistry. So the eruption begins down here with the yellow guys. Very cool. They've been sitting there crystallizing. Great, that makes sense. Next batch, okay, they're getting hotter. Already starting to overlap with Pu'o. That's interesting. And then we start getting into here, and all of a sudden, about 20 days into the eruption, we find olivine with almost 90% magnesium. Now that, you need a magma of about 1,300 degrees to get that. And this eruption is so disruptive to the system that it's scooping up some hot, deep olivines and mixing them in and carrying them down the pipeline. And they're growing rims, so the open symbols here are the rims. So when we actually zap the edge of the crystal versus the center. And those tend to be around this line. This line is sort of the theoretical line for what they should be. So it's telling us that most of these crystals, at least their cores, formed somewhere else. And then as they travel down, maybe they grow a little rim as they're going, and they're picking up this really deep hot stuff. So we have a whole other thing going on that you couldn't even really tell, except that magnesium went kind of wacky. So in yellow, that's our Leilani. The stank comes down, pushes the stuff out, starts mixing with it, hits this one, pushes it out, gets some mixing in there, and it's mixing with the 3, which is our summit Pu'o'o stuff. But somewhere along the way, it's scooping up some of 4 as well. One of our ideas is that this magma up in here, the shallow magma chamber, that was open to the air. That magma was circulating in the lava lake, and it cools, it degasses, it gets dense. And so when you start to drain that, it's denser than the lava around it. It's going to sink and potentially stir up deeper levels of your deeper magma body. And that's potentially one of the ways we may be getting those hot olivines mixed into the system. There's other possibilities, but that's one that seems quite likely.
So in summary, there were 3 sequences with this eruption. There was the Lower East Rift sequence associated with the intrusion of that magma and the opening of the fissures and the different phases of the opening of those fissures. There was the south flank sequence dominated by the 6.9 earthquake, and that whole zone of the south flank slipping on this almost horizontal fault beneath the island, and even extending far offshore. And then the summit sequence where the caldera was enlarging itself and becoming deeper and becoming what you can go see today.